There you go.
All right. Thank you for the introduction. All right. I think you all can see that. So yeah, today be talking about similarity search. I'll get into specifically how it's used in modern applications. It's a very big field. So I'm going to stick to what we're seeing today. What are the major use cases? So what I hope you get out of this talk is you have a better understanding of what similarity search is. I understand a lot of you are in computer science. Similarity search isn't necessarily taught in computer science. Um, but I want to introduce you to similarity search in sort of a unique way. I'm going to be talking about what I call the representation problem and the search problem. And that lets you sort of see where similarity search fits into these modern applications like text retrieval, image retrieval, and recommender systems. So that's sort of like the first part of the talk. In the second part of the talk, I'll introduce some of the open problems in the field where the research is being done in search and how my research fits into that in terms of graph-based similarity search approaches and parallelization strategies. So I don't need to give you this introduction about me, but something I'll say is my advisor at Brown is Professor Benjamin Kimia, and I'm a part of this Laboratory for Engineering Man and Machine Systems. And so an interesting thing about my lab is we're mostly for computer vision applications. And so I'm kind of the odd one out doing similarity search, but it's because similarity search has such far-reaching applications. That's why I'm sort of here. Another detail is we've had a collaboration with Dr. Chavez since 2023. We've published a couple papers together. And I'm an active member of the Similarity Search and Applications CISAP conference. So competing in the indexing competitions, and we hosted the conference this past year at Brown. So similarity search. So with the internet, we have these really large collections of data. So that can be images, it can be movies. With social media, it can be posts on X or Facebook, Instagram. All this data it's rich with information, but we need some way to process it. We need some way to look through it. And so when we say search, we're concerned with how do we find items in a data collection. And in computer science, there's the idea of you might want to search through a set to see if an item exists. And similarity search is it's a broader category. So it says it's not concerned with exact matches, but it allows for inexact matches. So I might want to find the objects that are similar to a query, and that might be the k most similar objects, or that might be all objects meeting some similarity threshold. And so, for an example that you're all familiar with Google, you put in a search term and it gets a bunch of search results ranked. And so here, similarity is measured based on keyword matches. So we're returning web pages if they have a lot of keywords that match our search query. But you can imagine that there's billions of possible web pages it could have given you, and it had to return this result in just milliseconds. A harder problem, maybe, is this reverse image search that Google also supports. So here, the query is an image, and it returns images that are visually similar to our query. And so there's no keyword matches here. And so similarity is measured based on the content of the image. So it's an interesting problem, and I'll talk a little bit about how that's done. Recommender systems is another really big application for similarity search. So if you go on YouTube, you'll get your homepage recommendations. And you can imagine there's billions of videos on YouTube, but how does it give you 10 or 100 to look at when you open your app? So in this case, you as the user, you're the query, and your search results are the objects that are relevant to you. And so there's sort of a few things going on here. So on one hand, you have the question of, well, how do I measure how relevant a video is to a user, or how similar two images are? And that's sort of what I call the representation problem. And on the other hand, if we have the similarity between two objects or between all objects, how can we efficiently search over this data set when it has billions of objects? And so that's sort of the search problem. And these two problems are focused on in different communities. So if you look at a paper that has the applications of similarity search, like a paper from Meta or Amazon or Pinterest, they'll talk a lot about the representation problem. They'll talk about, like Pinterest has a lot of great papers, and they'll talk about, they have this user item bipartite graph, and they use graph neural networks to produce embeddings. What they also do is they take those embeddings and perform search with them. But they only talk about the search. They mention the indexing part, the search part, in like one sentence of the entire paper. But the whole thing is similarity search. And so I was looking for applications last year of my research. I was doing a deep dive into all this. And so that's where I sort of came across this, developed this bigger picture of what similarity search is. It contains both the representation problem and the search problem. So to start with the representation problem, we need to define what similarity is. And so humans can measure similarity. And that's sort of the study of artificial intelligence, is how can we perform tasks like a human would? How can computers do that? And so one solution to measuring similarity is, well, what would humans do? And that's this cognitive psychology. It's a big study of this field. And so something, an early paper from Shepard sort of describes similarity as being this second order isomorphism. And that big word meaning the images or the objects are mapped to representations in our brain. And when we compute similarity, we're computing the similarity of the representations instead of the similarity of the underlying objects. And so this idea is based on the fact that objects are infinitely complex. And so maybe the representations are just some concise version of the object that contain the necessary information to measure similarity. And so in this case, there are sort of two functions we need to define to measure similarity between objects. We have this representation function, which maps objects to their representation. And we have this similarity function, which acts on those representations. And the goal to defining these two functions is that we want the similarity of the representations to approximate the true similarity of the objects. And so we don't really know the true similarity of the objects, but what we can do is we can implicitly define it. So, and that can be defined based on the task. So if you have a task like classification, I know that two objects are similar if they're of the same class. Maybe they should be identical, their representations. Or in question answering, an object, a document should be relevant to a user's question if it contains the answer. And so you can implicitly define similarity in that sense. And so the traditional approach to defining these two functions was handcrafted solutions. So people might take images and extract color information. Maybe they use color histograms to represent the images, or texture or spatial information. There's a lot of different handcrafted ways to make these representations and different similarity measures you could use. But today, and this was sort of the revolution of deep learning, for search at least recently, is that we now have these learning-based representations. And so the idea is that if we treat our representation and search functions as parameterized and differentiable, we can optimize these two functions so that the similarity of the representations matches the underlying similarity. And so that's a very high level view of what deep learning is. But that's what's important for similarity search, is now we can learn these representations for objects. And I'll talk about two prominent models for similarity. I'll talk about the feature matching based models and geometric models. So the basic idea of feature matching models, this goes back to Tversky in 1977, is that objects can be represented as sets of features. So that's sort of what humans do. When I had the slide up about dogs and cats, maybe you measured similarity based on they both have ears, they both have tails, a tail, they both have paws. And so the idea here is that you can represent your objects by sets of features, and you can measure similarity based on what they have in common or what's different. On the other hand, you have these geometric models of similarity, and this goes back to Shepard, 1980. And this theorized that objects could be represented in this high dimensional space, in this multidimensional space. And by embedding these objects in this space, now you can measure similarity based on proximity. So that's measures like cosine similarity, Euclidean distance, inner product. The benefit of geometric models is that they provide structure on the space. So a true distance metric like the Euclidean distance or L2 distance, it is symmetric, reflexive, and it can satisfy the triangle inequality. So that triangle inequality can be used for exact search, exact similarity search. So to compare these two models, and again, I'm bringing up these models because these are being used in applications. So what we see is that these geometric models are really what we're seeing today with similarity search. So a lot of some of you might be familiar with vector search. There's all these vector databases out there now. They support a lot of applications like recommendation systems. But the benefit of these geometric models of representing objects by vectors is that it's very memory efficient. So each object is represented by this compact vector. They're also computationally efficient, the distances, since it's just essentially a vector norm. The issue is that it's hard to store a lot of information in those vectors. And so they have a limited representation capacity. And also they can't model complex similarities. Like they can't model asymmetric relationships between objects that we see with human similarity. On the other hand, these matching models, since they take the two objects as an input, they can learn an alignment between the two objects. And that allows them to capture more complex similarities, such as asymmetry. The issue is that now each function evaluation is very expensive. And so what we see in application today, and this is the role that similarity search plays, is we have this retrieval and re-ranking strategy. So the query comes in and it goes through this retrieval stage where the query gets embedded as some high dimensional vector. It performs this retrieval stage using an index, which I'll talk about, and that references the data set to give us maybe 100 or 1,000 candidates. And so these candidates can be re-ranked with a more complex similarity function, like a matching function. And that outputs the final most similar objects. And so that's what we see today is this retrieval and re-ranking approach. And we see this in image retrieval, we see this in text retrieval, we see this in recommendation systems. We see these in a lot of places. And so that sort of covers the representation part, how we define similarity. Now I'll talk about the search problem. So this green box here, the indexing. So an index in similarity search is a data structure to provide efficient search that meets the constraints of the application that we have. So in modern applications, when we get our embeddings by deep learning, we're searching with high dimensional vectors, and we're using distance functions like Euclidean distance or inner product. To talk about some of the constraints that we might see. So the applications that we're dealing with are usually user-centric. So we want to make sure we get our search results without a delay to the user. So maybe that's 10 milliseconds. I think it's like a maximum of 50 milliseconds that people are concerned with, because this might be a part of a bigger pipeline. There might be more steps to do before it gets back to the user. So the search has to be fast. Another thing people are concerned with is throughput. So if you have an application like recommendation systems, you're not worried about one user, you're worried about a million users. So how many queries can you perform at once? And so this is sort of, I guess, adjacent to latency. You want to perform as many queries as fast as you can. Also, you have recall, which is your accuracy of your search. So obviously, 100% accuracy is best, but the data sets we're searching on are difficult. So we can get an improvement in latency or throughput by allowing for a lower accuracy, a lower recall. And something like recommendation systems, maybe you don't need 100% recall. Maybe you're fine with giving the user the third best item instead of the first best. But something like patent search, you might want 100% recall to make sure no one's thought of this product before. So different applications. And then index construction time, you want to be able to build your index in a reasonable amount of time, a few hours, maybe a day max. And you can search on all different hardware in terms of the memory you have, and then the compute units you have, like CPUs or GPUs. So in terms of indexes, well, the easiest approach to searching is a brute force search. So you can exhaustively compare your query to every member of the data set. There's no index required for a brute force search. It has 100% accuracy, but it obviously has linear complexity. So as your data set goes to billions of points, you can't perform this brute force search in any reasonable amount of time. I mentioned this though because for small data sets, like a lot of papers on image retrieval will use a brute force search because they want to know how good their embedding is. They're not concerned with how fast they do it. So it's tough when you go to read a paper like image retrieval. You might not think that it's an application of similarity search. It really is. It's just that they use a brute force search because the data set's small. But if they want to scale their problem, they're going to need some sort of index. This is where the whole considering both the representation and the search problem helps to see applications of similarity search when you're reading papers. But if we want to use an index, the goal of an index is to be non-exhaustive. So we want to search a subset of the space. And so in order to do this, we need to leverage some of the structure in the space. So that's where these geometric representations are helpful. Something like the triangle inequality. It lets us look at a subset, and we can organize our data set based on the structure. And so we might organize this like an inverted index, where we have keys that map to groups of objects in the data set, or we might use a graph. So my research is focused on graphs. I'll talk about that in a little bit. But these indexes can be used for exact or approximate search. So exact search, I mentioned you want to leverage some of the space structure in the space. So for the triangle inequality, we could use, with the triangle inequality, we could provably prune out points to consider. We could say that these points won't contain our neighbors because of this. On the other hand, you also have something like the KD tree, which some people might be familiar with here, but it used the assumption that the vectors, that the objects are represented by vectors, and you can partition along the dimension in order to find your objects. The issues with these sorts of approaches, these exact approaches in all indexes actually, is the curse of dimensionality. So, and that's the general term for the fact that the effectiveness of an index decreases as the dimension increases. Something we observe is that as the dimension of the data set increases, the distances tend towards the same value. So if we look at the plots on the right, the SIFT1M SIFT data set on top has sort of the distances, the pairwise distances are sort of spread out. As you go to the space V data set below, the pairwise distances are more condensed together. And when they're condensed, it's hard to differentiate points. It's hard to prune out points. And so that's sort of what leads to exact search being the idea is that you can't have an index more effective than brute force as your dimensionality increases. And the data sets we're working with today have very high dimensionality. So what we see now is a lot of approximate search. And so this provides a trade-off between efficiency and accuracy. And this is done with graph-based approaches, partition-based approaches, I guess, as I'll talk about here. So the idea behind a partition-based approach is to divide the data set into groups and search a subset of the groups. Pretty simple idea. What we mainly see today in this category is quantization-based approaches. So you might do something like clustering on the data set. You can get a lot of centroid vectors, and then each object, each vector in the data set can be assigned to their closest centroid, can be quantized to their closest centroid. And that defines an inverted index. So when the query comes in, it sees who its closest centroids are, and it can search the lists corresponding to those centroids. Examples of these are the face index and scan. Face is by Facebook, now Meta. Scan is by Google. The hashing-based methods also sort of fall into this partition-based category. And the idea here is that you have some hash functions that map similar vectors to the same buckets and dissimilar vectors to different buckets, and similarity based on locality. I'm not an expert on hashing based at all. I won't talk too much about them. But actually these hashing based approaches aren't too competitive in approximate search right now. It's mainly these quantization-based approaches and graph-based approaches. So to talk about graph-based approaches, this is what my research mainly focuses on. The main idea is instead of grouping objects, you sort of make connections between objects. So each object acts as a node in this graph, and you create edges to sit between similar objects. And in order to search, you search locally over the data set with the best first search. So if the HNSW there is a very popular graph-based approach using a lot of applications. Some of you may have seen it. But graph-based approaches are very successful in high-dimensional data sets. And so I mentioned that it's a best first search. And what happens is on each iteration of the search process, it chooses the neighbor that decreases the distance to the query. And so if you just keep choosing the neighbor and navigating to that decreases your distance, that's a greedy search. But that's highly susceptible to local minima. And in high dimensional spaces, we have a lot of local minima. And so an approach to get around that is beam search, which says, let's store a priority queue of all the nodes that we've seen, and we can backtrack to those nodes if we hit a local minima. And so that's the basic idea there. All right, so I have a bunch of slides on the applications of similarity search. I don't, just for the sake of time, I'm not going to go too in depth in these. If anyone has questions at the end, I can talk about them. But these slides get into, well, actually the background on each application. So the background on image retrieval, the background on text retrieval, and recommender systems. I'm just going to skip over a lot of it, and I'm just going to talk about the actual applications that we see of similarity search. So I guess I'll hover over it, but traditionally text retrieval has been based on keyword matching. Deep learning has enabled retrieval based on meaning or context between pieces of text. And so where this is being used today is obviously web search, as I mentioned. There's tasks like question answering, product search, type in a keyword in Amazon, something like that. A really interesting application is this retrieval augmented generation. So a lot of you are likely familiar with language models like ChatGPT. They suffer issues from having frozen knowledge, so they only know information up to when they were trained. They can hallucinate and just tell you the wrong information, and you don't really know where they're getting the information from. And so the idea of retrieval augmented generation is to give the language model access to a set of documents that acts as an internal memory. So when the user enters a question, it retrieves relevant documents from that knowledge store, then it answers based off that. And so it gives the user some more correct information, or it gives them at least they know where the user knows where the information is from. So that's the application of text retrieval. Image retrieval, based on the content of the image, not the early image retrieval was really text-based. It was retrieval by the captions of the images. So a way that image retrieval is used now is you can put an image through some, say, convolutional neural network, and you can use the intermediate layers or the fully connected layers as a representation of the image. And so some of these applications include, if you want to do duplicate image detection, something like copyright detection. I mentioned patent search, and then computer vision applications. So for example, the visual place localization. if you have a data set of images all over the Earth, and they're all images all over the Earth, and they're all geotagged, so they have some latitude and longitude, and you're given a query image, you want to identify a database image and then predict the location of the query image using that. Your database images also could be satellite images. So it could be finding the location of an image based on satellite imagery. So it's an interesting application. Yeah, so that's some of them. And then I talked about recommendation systems a little bit already. The main goal of a recommendation system is to give the users a good experience. So you have billions of options, say from YouTube. It's the role of the system to just give the user something like 10, something they can manage. And so each company has their own way of producing these embeddings for search. They all have their own papers that you can read. I talked about Pinterest. They have a lot of great research papers on that. And again, all these, the image retrieval, text retrieval, recommender systems are all using this retrieval and re-ranking framework for similarity search. There are some other applications that I didn't talk about. So instance-based classification, like a KNN classifier, if anyone's familiar with that. It's an alternative to a model-based classifier that you might see with deep learning models. Hard negative mining for training of neural networks. A lot of neural networks use this triplet loss. So you can take, say, 3 objects in the database, 2 which are similar, and 1 is different. And if you want to make sure that you want to improve how discriminative your model is. So you want to make sure that your object of a different class is sufficiently, it's hard. It's sufficiently similar to those other objects, but it's of a different class. And you can use similarity search for that. And another one is outlier detection for something like cybersecurity applications. So that's sort of the first part of the talk. I can go back and touch on any of those applications if people are interested. In the next part of the talk, I'll talk about sort of some of the research areas in similarity search, specifically in indexing. And then I'll get into some of what my research is doing. So the main goal in indexing is you want to minimize the latency or maximize queries per second for a given recall. So this plot on the right is from ANN benchmarks. It's a competition between a lot of different indexes. So say 20 in this case. And the x-axis is that recall. The y-axis is the throughput, the queries per second. And so up and to the right is better. You can have more queries per second for a given recall. And so that's the main challenge here is maximizing queries per second in this case. And this problem comes with a lot of different flavors. So you might have different types of search. You might want a KNN search or a range search. You might have filtering. So maybe you want to get objects in the data set that meet a certain criteria. Like maybe that's a certain size. If it's product search, maybe that's a certain size or a certain color, something like that. You can do search on different data sets. These data sets can have different dimensionalities, different scales, and you can do search on different hardware configurations, different amounts of memory, different types of computing power. So one of the biggest problems in search is this cursive dimensionality, which I already talked about a little bit. But how hard a data set is to search is related to its intrinsic dimension. And so intrinsic dimension is there's a lot of ways it can be defined, really. But it's generally what we know is that as this intrinsic dimension increases, there's more sparsity. So there's a lot more empty space, and that can make it hard for something like partition-based methods, which might have empty space, empty bins. That's what the KD tree suffers from. You can have neighbors in more directions. So now and directions in quotes because in metric spaces, you don't really have direction, but since you have neighbors in different directions, you have to search in more places. And also I mentioned that distances are converged to the same value. Their variance becomes tighter. And so eventually your index is no more effective than a brute force search because you have to compute too many distances. And so what we see in particular with these high dimensional data sets is that it's the high recall part, which is really difficult. So if you look to the right of this plot here, where we reach sort of 100% recall, this is about at 10 to the 3, so 1,000 queries per second. If I go back a slide, we can get 100% recall at 10 to the 4. So this is the same data set size, just a different data set. And this data set on this slide can process 10 times as many queries per second. And it's because it's an easier data set. Another problem is out of distribution queries. So there are some models that embed images and text into a shared latent space, and shared embedding space. And the idea is that you can perform image retrieval by giving a text query. The issue here is that the queries in the data set are of a different distribution. And this is difficult because the query is used to guide the search. The query is used to look at a specific set of groups, or it's used to navigate the search during graph-based search. But we're not looking for the query, we're looking for the neighbors of the query. And so if the query isn't close to its neighbors, then you're using a bad guide for the search. So it becomes a hard problem for these out of distribution queries. A lot of existing indexes are failing. So that's another area of research. Searching with different distance measures. So the Euclidean distance is widely used, has been used for a while. More recently, inner product has been used to train these neural networks, language models. And so now there's this maximum inner product search, which it's searching for the objects, maximizing some similarity rather than minimizing some distance. So it's the same problem, just a little twist on it. The issue is that the inner product's not a metric. So there's all sorts of things that come out of that. If you have an object, with inner product, you can have an object whose most similar object in the data set is not itself. It could be another vector with a higher norm. And so that can cause problems with some indexes. And then some indexes have been designed specifically for inner product search, like scan. Another really interesting research area that I found when looking at applications was this directly searching with neural similarity. So I mentioned before that we have this retrieval stage, which uses vectors, and then we have this re-ranking stage, which uses these complex matching models. And so the idea is, well, just use that complex matching model during the search. And so this completely skips the candidate retrieval step, and it avoids a re-ranking stage. And you just use this complex similarity function during search. The difficulty is now you have a limited number of distance evaluations. And you also have no constraints on the space. So it's an interesting problem, but it can avoid the re-ranking stage, which might save a lot of time. And there's a few papers that have worked on this. Another area of research is how to deal with limited memory when searching. So depending on your scale of your data set, you can have really big data sets. So for the indexing competition, I think the CICESE 2025 indexing competition, I think the data set's about 16 gigabytes. In CISAP 2025, the problem is limited to only 16 gigabytes of RAM. And so you need to fit the index in as well. So the idea here will be to perform some data compression to make the memory footprint smaller, so that you can fit both the data set and the index into memory. But some data sets, if you go to billion scale, or even Meta has an example for a trillion scale search, they have a data set with, it's 192 terabytes. And so it's absolutely massive, but they have no choice but to store everything on disk memory. And so one of the benefits of disk memory, even for smaller data sets, is that you don't have to perform data compression. Data compression implies lower accuracy because you're losing information. So with disk memory, you can preserve your accuracy, but you have slower read and writes. So something like graph-based approaches, graph-based indexes, which require random access of memory, can fail or are a lot worse with disk memory. Finally, parallelization is another interesting part of similarity search. So there's a lot of parallel hardware out there. So multi-core CPUs, GPUs. You can have multi-node systems that you can coordinate with message passing interface, MPI. To give you an example, I mentioned the trillion scale example from Meta, and they used a system with 100 nodes and 64 cores each. So that's 6,400 CPU cores that they coordinated to build that index and search with it. So you can coordinate a lot of resources. But what the parallelism currently is mainly being used for in search is for processing multiple queries at once. So you might see GPUs being used to improve throughput. But what my research is interested in right now is how can we speed up the search for a single query? So how can we minimize latency? And this will become a bigger issue as we reach larger data set sizes where normal approaches are reaching an unacceptable latency limit. And so, all right, at 43 minutes. So now I'll talk a little bit about my research. So what I'm interested in and what I've been focusing on for the past 4 years or so is this high recall search. So I originally started with exact search, and I sort of now interested in high recall, around 99% accuracy. Also interested in what is the optimal graph, or what are some of the optimal graphs for search? How can we build these graphs accurately and efficiently? And how can we use parallelization in search, as I mentioned? And so I already showed this visual of graph-based search. And if we want high accuracy search, there are a few things that we can do if we want high accuracy. We can reduce the amount of local minima, because if we don't have any local minima, then we find our nearest neighbor. Or we could use backtracking. And backtracking allows us to get around local minima. And both of these things increase the overall number of distance computations. We We might reduce local minima by increasing the connectivity, or we might, and when we use backtracking, it increases the search path length. We're searching more nodes. But if we want efficiency with our search, we want to minimize the number of distance computations. So that would be about, we'd want to reduce the connectivity of the graph. So we compute less distances on each iteration of search. And we want to reduce the length of the search path. So we compute less distances. So they're sort of opposites in terms of what we want to do. There's a trade-off between accuracy and efficiency. And so something I've worked on for the past couple of years is with this idea of monotonic graphs. And so the idea of a monotonic graph is it's a graph that removes all local minima for members of the data set, for queries which are members of the data set. So it allows for exact search if our query is a member of the data set. Unfortunately, it doesn't guarantee that for all queries. But the idea is that if a query is sufficiently similar to some database element, then we can mitigate the number of local minima. And so the other idea is that by treating database elements as queries and ensuring monotonicity, we can make our graph sparse by only keeping the edges that are necessary for monotonicity. And that it sort of provides this balance between accuracy and efficiency. I haven't answered if there's an optimal graph for search, but a monotonic graph seems to be up there for one of the best. There are generalizations of monotonic graphs, but those require adding more edges, which reduces your efficiency. So from what I can tell, the monotonic graph's a good balance. This idea of monotonicity is used in a lot of state-of-the-art indexes like HNSW. And in particular, one example of a monotonic graph is the half-space proximal graph. So I don't know how many of you are familiar with this graph, but it was developed by Dr. Chavez. And so that's something that we worked on in our first collaboration, was how to make the half-space proximal graph efficiently. And so that half-space proximal graph is built by this distributed graph construction, where on each node you apply this half-space proximal test. And it's sort of this test is sort of an edge selection algorithm. And I won't go into the details, but it essentially gives you a diverse set of neighbors in all directions. The issue is that it is computationally expensive. It has linear complexity for just a single node, so quadratic complexity for the whole graph. And so 2 years ago, we introduced the hierarchical HSP test, which allowed for finding the exact neighbors, exact half-space proximal neighbors in sublinear time. And then a subquadratic graph construction complexity. We didn't get theoretical guarantees on that, unfortunately. But the issue with this approach is that it suffered from the curse of dimensionality. So it doesn't really work on the data sets that we're interested in modern applications. I know I'm running out of time, so I'll go through this a little quicker. Another thing that we worked on for this past indexing competition was sort of this top-down distributed construction of proximity graphs, and so the idea here is that we use a top-down construction in order to make it distributed. So if we have this hierarchical organization of the data set, and we have this partitioning of the data set to the samples on the layer above, then we can use a graph on the layer above to help guide the search for a set of candidate neighbors on the bottom layer. And so the idea is that a graph above and a partitioning of the layer below allows us to build the graph on the layer below efficiently and in a distributed way. And so this can be useful. This wasn't very successful in the indexing competition because we were limited to 32 CPU cores. Where this could be more applicable is using GPUs or MPI to coordinate more resources. So that's on the docket to do. And the last piece I'll talk about quickly is I'll talk about what I'm doing right now. And so that's about parallel graph search. And so I already mentioned greedy search, and I mentioned beam search, which uses backtracking. The issue with beam search is that in order to get high recall, we need to increase the beam size substantially, exponentially. And so this increasing the beam size is increasing the amount of backtracking, which increases the overall latency. And the issue of beam search is that it's a sequential process. And so one idea, instead of doing backtracking, is to restart the search at a different node. And so then we can approach the query from different directions, and this can allow us to overcome local minima. The benefit of this is that, well, all these searches, each time we restart, we're at a different node. And if we do multiple restarts and they're all independent, well, we could just do them all at the same time from the beginning. So we can do multiple greedy searches in parallel from different start nodes. And that's well suited for parallelization. So there's a lot of parallel potential there. So with the GPU, we can leverage several layers of parallelism. Each search can be done in parallel. At each step of the search, we can do distances in parallel. And each distance itself, the vector norm, can be done in parallel. So I know I didn't talk about GPUs a whole lot, but they are really good at leveraging parallelism. Tasks that are parallel don't need a lot of independence. And so the idea here is that, well, instead of backtracking, which is the sequential process, we can perform all these searches in parallel, and the total cost of search is equivalent to the cost of a single search. And so on the CPU, right now I'm looking at the high recall limit. So we have 90% recall and 100% recall we're looking between. So on the CPU with a 32-core CPU, we can do 32 searches in parallel without an exponential increase. On the GPU, we can do about 2 searches per streaming multiprocessor, which is essentially related to the number of cores on the GPU. So given a maximum amount of searches we can do at the same time, we need to increase the accuracy of each search. And so the idea there is to, well, instead of just a greedy search, maybe one idea is to use beam search. So use a small beam size, a little bit of backtracking to increase recall. And so the results I show on the right is for a 32-core CPU. I'm working on the GPU implementation. But compared to just a normal beam search in blue, if we do 32 searches on a 32-core CPU, we can achieve 8-9 times speed up over just a normal beam search. Unfortunately, this idea that we sort of stumbled upon is actually very similar to what NVIDIA has done in Kagra this past year with their GPU implementation. So right now, we're working on a lot of different directions to take this. So that can include what's the optimal graph. It has this idea of creating disconnected components on graphs and searching on different components. We're looking at alternatives to backtracking and early termination conditions. So we have a lot of ideas there that we're developing. I'm going to finish with this, which is the sort of the motivation of doing parallel search on GPUs is that they're not necessarily affordable GPUs, but they're widely accessible. So they're used in a lot of deep learning and training models. They're out there. They're just not being used for search a whole lot. There are some approaches, but they're underutilized. And the main idea of our work is we're aiming to address the difficulties of high dimensional spaces and the fact that parallelization allows us to do more work. So rather than focusing on trying to speed up approaches by doing less work, let's lean into parallelization to do more work to reach those higher recalls. And this also has potential for different challenges like out of distribution queries and filtering. The disadvantage of this approach is if we're spending resources on parallelizing a single query, making a single query faster, then it prevents those resources from being used to process multiple queries at once. So we're minimizing latency, but we're not necessarily maximizing throughput. And so that's something that we have to consider and we have to look into more. The other issue is GPUs have a limited global memory. The H100 GPU has 80 gigabytes of space, so are limited to data sets of 10 million, maybe 100 million. So another question is, how can we perform on larger data sets? And I mean, this is just a summary, so I think that's about it. Thank you.
Thank you for your presentation. Well, we're still on time, so we can go with the round of questions and answers. Okay, Mr. Cole, my question is related with something that you mentioned about satellite images. You were talking about similarity search in images specifically. Yeah, I don't know. Well, this is a wide question, I think. I don't know. What other applications do you see for your research in geographical information systems? Not only related with satellite images, maybe something related with GPS data, that kind of stuff. What other applications do you see for your research on that?
That's a good question. I haven't looked a lot into that sort of field. What I do know is that I've been looking into really big data sets. So we're working on what happens when we reach trillion scale. And so something that I am familiar with, at least I read a paper or two, is there's really large collections of tracking data sets, like GPS tracking. So that might be used if you're trying to track exposure to, say, a disease in a city, and each person has a cell phone, and you have these, and you have their positions within the city over time. So you get these really large data sets. So it could be a search of over where are people intersecting and where possible exposure contact could have occurred.
Okay, I got another question. This one is related with the parallelization. You mentioned that you are somehow doing some parallelization stuff related to GPUs. Have you ever explored, or do you have in mind to explore different technologies for this purpose, maybe FPGAs or something like that?
So there are papers doing search with FPGAs. I'm not familiar with them. I know there's been a lot of success with that sort of architectures, but I'm not familiar with them. Obviously, I don't know much about them, but I know that they're sort of customized. So I'd say they're definitely probably able to perform better than GPUs if you're able to customize them a little better. But it's not something I'm, I guess, working on right now.
Okay, great. We have a question here in the chat. This is from Andres Herrera. He says, you mentioned two distinct representation models. Do hybrid solutions exist? I believe you mentioned something along those lines with group partitioning. Could you discuss that further?
Okay, so my first question, if I can ask a question back, is do you mean the representation models of do you mean partitioning versus graph-based in terms of indexing? Or do you mean in terms of geometric versus feature matching? If I could ask a question back, Andre.
Yeah, that's a question for Andres.
Yes, hello. Yes, I mean more so along the lines of geometric versus feature matching.
Okay, yeah. I'd say that's a really good question. I think there is a lot of overlap. So for one, you could interpret something like the inner product as being both a matching model and a geometric model. I mean, you have these high dimensional vectors, and when you're doing a inner product, you're comparing if two features along those vectors are similar. And so you also have something like you can have sparse representations, these sparse vectors. And if you have places in those vectors that contain the same feature, then they sort of then that inner product increases because they have the same feature. So that's sort of a matching model. You're looking at matching features, but it's still technically embedded in this high dimensional space. So that's one place where they exist. Another place where they do exist is I mentioned the searching with neural similarity. And in that case, the inputs to the neural similarity model are still high dimensional vectors in those applications. It's just now they have a more complex similarity function. So it's like the objects already exist in sort of this geometric space, but now the similarity function, which can act like a matching model, is a little more intensive and it can give better results. So these definitely aren't distinct categories. And there's also other categories as well that I didn't talk about. But it's a good question.
Great. Thank you. There's another one. This one is from Luis Alonso Gallardo. It says, why looking for maximum similarity instead of minimum dissimilarity? Minimum of dissimilarity is 0. Maximum of similarity is image dependent and thus unknown. In geophysics, we are using outer products instead of inner products a lot in multi-physics. Complex one.
Yeah. So something about these models these embeddings that we're using is that they're coming from these deep learning models. And they're trained to satisfy a certain similarity measure. Right now, they're all being trained with inner product or cosine similarity, some with Euclidean distance, but that's less popular. But it's sort of important that you stick with the measure that they're being trained in. If you remember that with representation learning, I sort of said we're propagating the error backwards. And so if we fix our similarity function, if they fix it as the inner product, then we have to sort of stick with that inner product when we're computing similarity down the line. I'm not familiar with anyone using outer products or anything. That could be an interesting space.
There is this area of non-metric similarity search, or the similarity search, and it's if it is difficult to have high recall in similarity search, it is even more difficult when you don't have a metric. That's just a comment to Luis Alonso.
I'll read it in Spanish. El Centro de Investigación Científica y de Educación Superior de Ensenada, Baja California, otorga la presente constancia a el Dr. Cole Foster por impartir el seminario Similarity Search in Modern Applications. And it is signed by the big boss here, which is Gilberto López Mariscal.
Awesome, thank you.
Thank you very much.